we started with descriptive, inferential statistics, and we saw that we can use different statistical techniques to test whether there exist differences in the sample mean. And among the tests we saw the one sample, which we all agreed that we use it where we have a test value. That test value could be a hypothesized mean or the population mean. If we have the population mean, we give an example. We saw that once you have a sample that you want to verify with an existing standard, then such a test becomes ideal. Then we went further to check the assumptions, which we say that as a statistician, one of the most important things you do is to verify assumptions concerning a test before you use it. And so we took time to see the various assumptions that are when we are dealing with one sample. And one of the assumptions was that the dependent variable should be continuous. In other words, we are saying that our test variable should not be categorical. The second assumption was independence of observation. The third said we should not have significant outliers because they basically distort the data, and so the mean will not be at the center as a principle. We equally said, apart from testing for outliers, we also try to look for whether the data is normally distributed. In other words, normality and distortion of data are not exactly the same things. We can have outliers in our data and the data is still normally distributed. And I said one of the two last assumptions are very important because they cut across most of the statistical techniques that we'll see. That has to do with parametric. Are you using ANOVA? Are you using bed sample, independent? Maybe regression. With regression, there are more assumptions to be verified that beyond what we have seen thus far. But it is very, very important to know that you need to test for those assumptions. And only when the assumptions are confirmed can you use your results and know that they're reliable. We saw an example. And in the example, we saw that a company had a challenge. They are given specification for a producer of disc brakes to produce some brakes and give to the company. And the producing company had different types of machines that were producing the same brakes. When the company collected the brakes and tried to fit in wherever they wanted, there are some challenges. So the quality control department discovered that there were issues with the brakes. Some of them were okay, but some were not. Some were more than expected. And so, as a quality control measure, they apply what we learned earlier, which has to do with random sampling. That randomly selected samples from the different machines to test and see if the produce from the machines significantly differ from the expectation. And so after testing, after collecting the data, it was given to a statistician who did the analysis. And so from the analysis, the conclusion was that some of the machines are doing well, but some, they produce exceed expectation. And so they need to be discarded. We equally saw the necessity to be able to format our data accordingly, and to learn how to use upper style. We have the auto table content, table formatting, and those are little things that are useful to make your work look presentable. So that's what we covered yesterday. Today, we want to add to what we learned yesterday, which is under mean compared. And I believe it will not be very difficult, just extending what we've learned on one sample. Yesterday, we were dealing with one sample, and like the name suggests, we're dealing with a single group. But today, we are looking at the two samples, which has to do with at least two groups. So let's assume that you are the principal of the same molecule. And as a principal, you have repeatedly discovered that students from 5A are underperforming compared to those from 5B. Seemingly, you are not, there's no, at least there seems to be that the performance of the two classes are different, right? But you're not sure if maybe it's just a random error because of your sample, or there is an underlying differences within the two, in the performance of the two classes. So in such a hypothetical situation, you are the principal who needs to get data. Once you get the data from the two classes, you have to compare the performance of the students. Now we say you always have to start with understanding the underlying assumption. And the assumptions are the hypotheses. So you have to state your hypothesis. And the hypothesis in this case could be that the performance of the two classes are the same, right? Stated in the form of U1 is equal to U2. So the performance from group 1 is equal to the performance of group 2. In such a case, we say this is a null hypothesis. We are assuming equality. No group is performing better. Now we said once you state your hypothesis in this situation like this, where we said one is equal to the other without taking any direction, we said it's a non-directional hypothesis. And so we are expecting that it can be equal or different. We've not taken a side to conclude that from 5, maybe group 1 performance is greater than group 2. We've not decided. But if we are to decide that the group 1 performance is higher, or is higher than group 2, our hypothesis becomes directional, which will state that it therefore means that the performance of group 1 is greater than or equal to 2, right? Yes, so it can be greater than or equal to, since we have taken side. So that is the first thing that you need to understand, that you need to state your hypothesis. It's only when you have stated the hypothesis that it gives you now the liberty to go ahead and analyze your data. So as a statistician, one of the things you do when you're analyzing your data is always have to have at the back of your mind, what hypothesis am I testing? What's my objective? What's my hypothesis? Because many times we can collect data for a lot of things, right? You don't have to go and be analyzing data just for the sake of analysis. Your data is driven by what you want to verify. So you have to state your null hypothesis and your alternative hypothesis. So we say most of the hypotheses traditionally are tested at 95. So most statistics will talk of 95% confidence interval. We say the confidence interval is a range of values for which, if your results fall, you say they are by chance, right? Out of that zone of chance, then you can conclude that there's enough evidence that whatever is happening is no more by chance. We can recall the examples of Peter, right? This is how we got to a point and became very angry. That Peter made a proposal which he knew that would favor him. But he told us that it was a fair game. So we must take into account. So we are testing at 95, but we can also test at 99. We can also test at 90. Now, if we are testing at 95, then our alpha value will be 0.05, right? So if you are testing at 95, the rule of the thumb says that for you to decide whether your null hypothesis should be rejected, or at least we must use attempts. The p value that you get, let's call it p calculated, should be what? Less than 0.05. So when you run your statistic in SPSS, you see sig. It stands for significance and it's equal to the p that we're talking of. So which means your p that you calculate should be less than 0.05. That's the first thing that I need to emphasizing this because I discovered yesterday that some persons are finding challenges. And it's the same mistake that Elizabeth did when she was doing her assignment. So you must compare now with 0.05. Now, comparing with 0.05 is not the only thing that we use to do the comparison. We can use the t value, known as t statistics, to draw that conclusion. In other programs, they'll use the critical ratio, CR, right? All of this, they're helping you to draw that conclusion. And most of when they're using the critical ratio, you'll see 1.96, I think 1.9 plus or minus 1.96 will be our test value. We want to see if your value is greater than this, right? It means your results are significant. If it is less than, they're insignificant. That's why the higher your test value, the higher the probability that the results will be significant. Do we get that? So we can use a critical ratio. We can use the t statistics. They're almost the same. We're using chi-square. We use the chi-square distribution to check. And in some cases, we use the confidence interval to do that, which means we're using the upper and the lower limit to draw our conclusion. You get it? So when we run a test, we'll see how all of this, they help you. You don't need all of them to take a decision. One is okay, because the results will be the same. So you don't need to go and be putting all of them in your study. So having said that, we all agree that we need to have what? Our hypothesis. And once we have our hypothesis, we can now go ahead to test our data, right? As we have indicated, this is a possible way that your null hypothesis should be stated. There's no differences in the mean. So U1 and U2, they all stand for the mean, right? But the alternative says there are differences. It can be equal, it can be. And once we want to use the independent sample in particular, you need to ensure one of the things that you must always look out for is that you have at least one categorical independent variable. I repeat, one categorical independent variable. You must have at least one categorical independent variable. And if I want to add a statement to one dichotomous independent variable, it means the categorical variable should be what? Dichotomy. It has two options. It could be a yes or no, male or female, right? Pass or fail. So your independent variable should have at least two groups. That's what we're saying. Group 1 and group 2. Then your dependent variable must be what? Continuous, as we saw. So that's kind of checking for. So you must have at least one dependent variable that is continuous. That's why here we talk about the binary. The independent variable should be binary, which means If your independent variable is not binary, you cannot forget about using the independent sample. We will get that. So that's the first preliminary check that you must ensure. So it's like already talk about the first assumption. So if you see from my slide, I simply said before you run this test, you must always check this assumption. I'm using the word must. If you want to be a professional, but you don't want to be a professional, you can ignore. Yes. So you check to make sure that the assumptions hold. But then it's important to note that in real world, the data then becomes complicated. These assumptions might not hold as we expect. So some of the assumptions might be violated. We may not hold strictly. Do we get it? So that's something that is important to take into account. So we have already discussed the first assumption, continuity of continuous independent variable, 2 categories for the dependent variable, and there must be what? Unrelated. The word unrelated is very important. That is independent. There must be 2 independent groups. If the groups are not independent, you cannot use a test. I believe we know what independence means. Pardon? They're not related. It's the same thing as a member of group 1 should not be in group 2, right? In simple terms. So just to note that in case if your groups are more than 2, then you may use ANOVA. Yes. So which means instead of testing for group 1, group 2, or from 1, from 2, I mean from 5A, from 5B, as we've just stated, we had up to from 5C, and you wanted to verify, then you will go for ANOVA test. Do we get that? Right? So that is the second key assumptions you need to verify. Now, the next thing to also verify is this one. And we already indicated that this assumption is vital for all parametric analytical techniques. So we know that when we talk of outliers, we are referring to values that deviate from the normal. We give different situations. I think it should be in this class that we said, let's assume that you are looking for countries, list of countries, and you see a town there. Well, that's an outlier, right? And such an outlier, the way to treat it is to delete it, right? But then if you are calculating the incomes of civil servants in Cameroon, we assume that the average income is, I don't know, 200,000 francs. Let's just say it's 200,000. But then there are 5 ministers who they also consider themselves as civil servants, and the government is paying them per month 5 million. So they become outliers as well, extreme values. They deviate from the normal. So do you delete or you maintain? Well, the peculiarity of the situation tells you whether you should maintain. For instance, you may maintain and change, instead of using the mean, you use the median. That's another way you want to manage the issue of extreme values. So the median becomes the ideal measure of the central situation. You may have to transform the data. We'll see data transformation. So treating of outliers is mandated by the case that you find yourself. Now, apart from outliers, there is another assumption that you need to verify, which is that of what? Homogeneity of variance. Homogeneity of variance. Now, homogeneity of variance, we already know about variance, says that the residuals from our measures should be a kind of similar, right? Which means when in other words, they're simply saying that the 2 groups should come from the same population. Let me put it that way. right? Now, the two groups coming from the same population means they have something in common. They're not totally different, right? They have something in common that gives them the liberty to be compared. You don't want to compare apples and oranges. And if you want to compare apples and oranges, you also need to identify an area of comparison. Are you comparing the sweetness, the color, or whatsoever, right? Yes, so that is a principle. It's both here. Since you're comparing to male and female, but they should share something in common. Maybe it's the performance, they're in the same class and going through under the same conditions. To do that, we're trying to test for homogeneity. And so there is a test that we will see called the Levene's test of equality of variance. So to check for homogeneity, we use this test. So we have seen first, we have to check for outliers. We know how to do that, right? Cameroonians, we know how they test for outliers. That extreme value there for data, so I know how they test that. Eh? Okay, we should not bother. We should not know, eh? Nobody should know. So, since we don't know, it's okay. So the next thing you need to also verify is what? Homogeneity. Once you are done with that, you cannot test for normality. So we could say this is the assumption to be verified. The fourth assumption, which is homogeneity, and we'll use the Levene's test to do that. And so this is the fifth assumption of normality. Your data should be normally distributed. We know what it means. If the data is not normally distributed, you can transform the data to be normally distributed, or we use the counterpart non-parametric test, which is the Mann-Whitney U-test. So which means if you take your data and discover that those assumptions there were outliers, the data is not homogeneous, and so the data is not normally distributed, you either have to transform to deal with outliers, transform the data, or go for non-parametric counterparts. Right? It clear? Okay. So, as simple as that, any worry with respect to the independent sample test? Any worry? Any worry? So, don't say that you were not taught. When tomorrow you see tomorrow you hear that they're talking about two sample t-tests, independent t-tests, or student t-tests. They're referring to the same test. Right? Just let me emphasize it because there's a tendency that somebody will say, no, there's nothing like. So you can call it a student t-test, or independent sample t-test, or the two sample t-tests. So how do you do that in SPSS? I think it's quite easy, right? Even without us taking exercise, you know how to do it. That's what we agree, right? But the key thing is for us to identify the test, its application, and how to do it in SPSS. And then writing our results in a standard approach. So we already know if you have learned SPSS for a day, you know how to use it. Compare means, go to. And so let's open our data and see how we can do it so that we practice what we've learned. So now we have our data here. And we have height and we have weight. There's some variables that we pick out. Now, I want us to do a few thinking. Let's look at height. What would be our hypothesis if we wanted to consider height and gender? What should we state as our null hypothesis? What would be our hypothesis, especially the null hypothesis? I didn't get to. Be audible. You know there are others online. So if you're saying something offline, be audible so they can get. Okay, she says the male will be taller than the female. Ah, okay. Another person with a contrary view.
For me, the null hypothesis should be if both male and female gender have same height or similar heights. So there is not really like someone is more and some gender is more than the other.
Okay. We have two suggestions. One person says the heights will be the same. But another person argues that male will be taller than female. So who is right? Addison, what do you say? The first, male taller than female? You don't know yet. What is your expectation? It's an assumption. We're stating assumption. We've not verified. We want to state our null hypothesis. I want to state our hypothesis. And we've collected data. But before you even collect data, you need to have an expectation. Generally, what do you think will happen in the real world? That's how assumptions are built. You know? Male will be taller. It will be the same. Is it biased? Female will be taller than men. Male will be taller. Let's check in this class. Who is the tallest person? Who is the shortest person? Who is the next shortest person? So there's a possibility that in real world, it's not the representation, right? We acknowledge that. But at least we have a sample to start from there. So all the two hypotheses are okay. It depends on which one you want to take. Do you want to assume that they're all equal or they're different? Most of the times we assume that they're equal. That's our null hypothesis. We don't want to take this because we have an idea that men will be taller than women. But if you do not know, you assume that their heights will be the same. So let's take weight. What are our expectations with respect to weight? Will the meaningful weight for male be the same for women? Be more or will be less? Women will have more weight than male. Those online, do you agree? I continue by the same principle. But Erika, thank you for joining us today.
Is it still the null hypothesis?
Well, we just want to look at height and gender. I mean, weight and gender. What's your take?
I think
will the weights be the same or they'll be different? And if they're different, who will be more than the other? Come again.
The women are different and women will be more than the male. The weights are going to be different and the women are going to be have more weight than the male gender.
Okay, let's verify again. Real world scenarios. Who carries the friend most of the time? You don't carry something that's more than your weight. That's why we're talking about weight. You needed to take into account the differences in the bone. That's why hypotheses are built. They are not built from space, right? So it will be difficult for the weight for women to be more than that of men, because in real world, men, even a small man will carry a very big woman. So because of the differences in.
So what about the fat?
We are not measuring fat. If you go to size, women, I believe women will have more size. We're not talking in terms of size. Maybe you took size to mean weight.
Okay, yes, I think so. Yeah.
Yeah, so we're just trying to not analyze our data, but we want to see how statistics work. It's not something that's so much in a space. So for our expectation, we think that our real world situations, generally, a man wants to be taller than a woman. That's why even in terms of marriage, women want that their husband should be more than them. It's hardly the other way around, right? And away from that, if you check, men tend to be taller than women. Yes, generally. The average difference might not be significant, but then in most scenarios, right? Same for weight. Just the fact that a man can carry a woman easily and a woman will find it difficult to carry a man tells us that their weights are, because weight has something to do with carrying. You get it? If somebody wants to disagree, there are exceptional cases, significant outliers who. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah. Do you have a case too? Because you have seen somebody with, well, I might not want to argue, but generally, we're looking at general situations. It might be exceptional. I know that men easily carry women because they have more weight. They can be exceptional situations. They have more stability. It's difficult to carry something that is more than your weight. It's difficult to carry something on your own that's more than your weight. Yes. So that is the principle. So basically, those are our assumptions. That's how hypotheses are developed, right? That's why when you are doing studies, they say you don't go and take things from space. It must be at least a theory or empirical evidence. What is our here? We're dealing with what? Theoretical expectation. Given the prevailing circumstances around us, our expectation is that the height of men should be taller. And men should be more than that of women. That's our expectation. Data may disagree, but we had an expectation. And see what's happening. Village people are calling for you. Are village people calling for you? So that's the basic ideology. So let's go and verify our assumptions. Unfortunately, I'm not using bot again for people online. I've been drawing some of those things online. It's fine. So we go to compare means. We are dealing today with one independent sample t-test. And so there we take. So let's take the first one to be height. Now this data, what's the average? What would be the average human height? What would be the average human height? Let's measure it in centimeters. Or in meters. You choose meters. 1.5. 1.58. That's for men or women. Let's share. Let's divide and see. What's the average height for men or women? The average height for men will be up to 1.7. 1.6. Still high. People like Derek will bring down the average. So the first thing we need to do, this statistics, that's he's talking, I'm not the one. Statistics, the first thing we need to do is to explore our data. We'll start with the assumption. We don't just go to run the test, right? We have to check the assumptions. So the first assumption is that we should do what? The dependent variable should be continuous. We affirm that the independent variable should be categorical. I think we also agree with that, right? So that two assumptions are. The next is to check for significant outliers. How do we do that?
We go to analyze.
Yes.
Descriptive statistics and click on explore.
Explore. Beautiful girl. What's your name again? Yes. What do we do now? We end at explore.
We take the dependent variable.
Yes.
So I don't know which one we decided is
what do we hide?
dependent variable. So we drag the height and paste on dependent list.
Okay. What should we do next? I don't know.
And then we click on statistics on the right, and then check the box of outliers.
Okay.
Click on statistics, yes.
Okay, I'm already at outliers.
I click continue.
Continue,
and
yes.
then we check on plots.
Okay, plots.
Click on plots.
Yes.
So our stem and leaf are already checked.
Yes.
Then we also check normality plot with test.
Okay, we take normality plot with test.
And then we click on continue.
Continue. Okay. What do we do now? What do we do? We paste?
No.
I take options.
No.
Okay. We take okay, I'm sure. Right?
Yes, okay.
Is she right?
Because we are looking at the variable height, yes. So
yes. I'm asking your colleagues if what you just explained is the right thing to be done. Okay. Somebody saying something. So what should we do? Independent list we should add. Where's independent list? Okay. You say independent list now. Okay. Do we agree? The override part of your conclusion, they say we should
add the factor list.
Yes. Do you think he's not misguiding us? Do you agree with him?
I don't really know well myself, but I think that the person is maybe thinking we are looking at descriptive, the descriptive box where you can put the variables from dependent and independent. But I don't know if when we are trying to explore, we have to also do that.
Okay, since we don't know, let's take okay and see. The disagreement is coming in late, so. Nothing happened. Any changes made to the working files have been lost.
If nothing happened.
Village people have taken away my dog. I said it. This one he started behaving strange like that. And it's affecting my data set. Just stop that. It's just an outside. That means try to save the data somewhere.
I think in crosstabs there's the dependent and independent where you put them in a column and in a row. But
are you taking us now to crosstab, madam?
No, I'm just saying that maybe this person.
Same scenario. Somebody should run the data, please, and see. It came out well. So interpret for us, sir. You need assistance. So the person who assisted you should go ahead and do the interpretation. While I try to verify my source. Are you doing the same thing, Ekon?
Yes, I already have the.
Okay, just do the interpretation and you teach us today, please.
No. Hey. You have to enable me to share my.
I want to meditate.
No, you have to enable me to.
Okay, to share your screen.
Yes.
Go ahead. You'll be granted access.
So the first was mine, I put only the height. And then the second assumption thesis is the person who said for the height and the factor list gender. So this is it.
Okay, start with your own. Let's see what came up, the first one that you did. Yeah, I think. Yes. So, what's the average height? 68 point. This American measurement of height, so it might not align closely with us. I don't know whether you're using inches or what. What's happening? Yes, continue, please.
Our own, yeah.
So, check for normality. How do we do that? Screenness and are you disconnected? Go down to the first way we can check for normality is to look at the skewness and scattering. We say the value should be between -1 and 1. Some people take -2, but then -1 and 1 is most ideal. Extreme situations out of 3. So we think that data is normally distributed, right? Okay, continue. Let's see the other part. So we seem to have a few extreme values. Participant 3, 26, a height of 84. Participant 3, those are the top 5 highest values and the top 5 lowest values. Yes. So we may have some extreme values, but data normally distributed. What's the answer? Kind of. Although Shapiro and Komogorov seems to be disagreeing, we know that the sample size is more than 30 or 50, so it starts being sensitive. So continue. So go down, go down, go down. Yes. Wait, let's see. 4 extreme cases. There are some extreme values with their height more than or equal to 82. Yes. Continue. Let's look at a plot. Fairly normal, except for the 2 extreme cases. Yeah. Pure plot or quanti plot, they call it. Continue. I hope we are understanding what is happening. This is almost the same thing, but just represented now. The line of best fit being horizontal. Yes, continue. You've seen the extreme cases. So we have about 5 or 4 persons that seems to deviate significantly from the standard. Our data shows that it should be, I think, positively skewed or so. Let's continue. So that's the situation. So we might conclude that the data is normally distributed with some few outliers. So we can still go ahead and use the data as such. But then the second proposal was equally good in that while we are trying to check for the overall normality, it gives us also a possibility to examine whether that normality differs with the different groups. That's where we have the factor list. So if you check now, let's do comparative analysis now. The height for men, we want to verify our assumptions. The height for men, average height for men is 92. Average height for women, are we right? No, that's not height. It's not, that is not valid. I think case summary are giving kind of frequency, missing values, and the rest. Okay, sorry for that. I was surprised that our assumptions are faulty when we're not even. So continue. So the average height for men is 70, for women is 65. So at this point, what do we say? Men are generally taller than men with a, let's check the standard deviation and see. What's the standard deviation? The standard deviation is 5. And for women, variation in height will be higher in men or women. Higher. Okay. We generally tend to have very short men who are down there. And then tall, some of us who are up there. Right? Okay. So we are concluding that variation is higher. We can data also support, I think. Go up a bit, go up again. Okay. Yes, this table, we're not done with it. For men, what do we make again from these statistics? The gender distribution, I mean, the height for men is positively skewed. But for women, it seems to be negative. It's negative for women. So those are things you are looking from the data. Right? So if it is positive for men, it means we tend to have more of, I think, more tall persons will be above our mean. That's the expectation. And for women, since they will tend to have more short persons than who have, it's data they're saying, not me. I'm just interpreting the data. So nobody should be angry. So the variance, we've checked that. The range, let's see, the range for men is 23. For women, what is it? 22. So it supports our idea that variation is higher for men. So let's continue. Yes, we can go and check the extreme cases for women and check for men. Yeah. not unnecessary now. But we could delete the, one way of treating the extreme values is to delete, but you don't want to delete most of your data. That's also another challenge in statistics. So we don't want to. So I've not seen some plots. Continue, let me see. I've not seen QQ plot. We did not take it. We needed to take QQ plot, but although we have already seen, so it's okay. I think that should be all for now. So the next thing is for us to go back now and verify the assumptions. Is to go and examine the test. It's okay. This is okay. So we have the significant outliers in the group of, should be women. That's the expectation. Even without seeing the label down. I can't see the label, but I know that should be. Good and a bit, let's see the label. What's the label? Always be women. It's obvious. You know, we have some tall, huge ladies, like our first lady. So they're the ones that form this category, right? They're not only tall, they're huge. So those are extreme cases, right? Generally, men, they're almost, they don't have extreme persons. So that's what the data says. So let's go back now, go and run us the independent sample t-test, and we draw our conclusion. You can take analyze, or you go back to your data yourself. Minimize. Keep it a small, this thing is analyze. Independent, no, we don't need to explore again. Compared means independent. Yes, okay. Now, take height to the test variable, and then gender to the grouping variable. It's like you have learned computer using programming, which program? MS. Click on define groups. If you don't define groups, okay button will not come. You need to define the groups. Click on define groups. Yes. So we have 0 for no. Put 0 in the first box. Those are our values, and then 1 in the second box. And we want to differentiate so that the system should be able to identify who is a she and who is a he, or the groups that are involved. So take OK, continue. Go to options. Let's see. Let's take the default 95. So just take continue. We can deal with missing values using the case-wide or this way approach. So hammer us with OK. Okay. So the first results go up a bit. So can shift down. It's still a normal descriptive from what? No, just the recent results, please. Yes, it's just I don't see the entire table, so I don't know why. So we have already seen that male generally taller than women. The differences of about 5 for men and 4 for women. That's the standard deviation. Then I can't see this table, the next table. I don't know why. The independent sample table, we don't see all of it. Okay. So it's okay now. So we have our homogeneity test, right? It comes with F value and its probability. The F value is similar to T, as we're seeing. There's some tests that we use with F, the Fisher test, that test for homogeneity. So in regression ANOVA, we'll have it. So we have the value and its probability. The probability is 0.72, right? Which is insignificant, which means equal variance assumed hypothesis is true. The variance from the two groups are almost the same, right? The variation across the errors are almost the same. So they probably come from the same population. That's what we're trying to establish there. So once we test our, we use our test of homogeneity and it's significant or insignificant, we'll go ahead to interpret the first part of our results. In which case, we'll now look at the t value, its t and its value, degree of freedom, and then its probability, right? Now, if you look at the t, you see there's 10.486 with a degree of freedom of 397 and it's significant, right? So, what are we saying? We see that there is a significant difference in the means, right? And the conclusion from it is that men are generally taller than women. If our test of equality of variance was not significant, we'll read by the second part of the results. Although, from my experience, most of them always align. But the only thing that I've tried to correct for what that variance by reducing a degree of freedom, right? But in most of the tests that you find, they will always give us similar results. So you want to report your results, you also have to bring in the mean difference. What's the mean difference? The mean difference is the difference between this and that, which is 4.8 centimeters or whatever we're using. And then we have our upper and lower limit confidence interval 95. It tells us that we have 95% confidence that the mean population mean for men and women for somewhere between 4 and 5. Or in the confidence range of these values. That's what we are trying to establish. So we conclude that men are generally taller than women as shown by our results. So that's all what independence t-test seeks to achieve. So let's quickly just test the next one. Just go to analyze independent sample t-test, take weight. Let's see that. And I expect us to move from here. Yes, it's okay. We already know what to do now. Remove height, just remove height. Don't remove any other thing, just remove height. Bring in weight. Just take off the thing, everything maintain. So what's the situation? Weight. Do you still get plenty weight now? They eat a lot. So what do you expect from people that eat so much? So I think we are very much explicit with this test. Anybody with a challenge as this test is concerned. Now we could equally use the upper and lower, limits to conclude our test is significant. The rule of the thumb says if we have all the upper and the lower, they are positive, then our test will be significant. If they are positive, negative, they will be insignificant. In other words, if they don't cross the value 0, they'll be significant, which means negative, negative is significant, positive, positive, significant, positive, negative, insignificant. You can use that to conclude. You must not only use by probability. That's why I said there are different ways. At least for all these other tests, it may be slightly different when you go to something like non-logistic regression where the rule changes a bit. But if we had the lower limit to be negative and the upper limit to be positive, our test will be insignificant. Okay, crosses 0. If we had negative, negative will be significant. And since we are positive, positive, we know that it's significant, even though we don't have the p-values and the t-values to draw that conclusion, we can still be comfortable. So thank you very much for that job. Well done. So
welcome, sir.
The next thing, I just want to, let me share my slides again. Share it so that we've seen the application, how to do it. So that's what these slides were all about. So there is output of SPSS. From SPSS, when you want to report, normally it begins with the descriptive. We saw it, mean and standard deviation for our variable, right? Segregated with respect to the categories. It helps you to have initial descriptive. Remember, we always have descriptive analysis whenever we are doing. We always have to have some basic descriptive so that we have a pre-knowledge before we verify. And from the descriptive, we discover that men were more than women as height is concerned. Then the next part that you see has to do with we talk testing for quality of variance. We've already explained that. And so how do you report your results? Right? In reporting your results, it is important for you to talk about this test, right? It's important for you to talk about testing for normality before you present your own findings and also bring in the descriptive. Yes, it's always important. For instance, when reporting, just reiterating what I've already stated. So if you want to report as a pro, then you need to provide enough information for your reader, and that information will include you tested for normality, you have to mention whether there were no significant outliers. If they were, how did you treat them? Then you have to talk about the mean and standard deviations from the two groups, right? You have to report the mean and standard deviation from the two groups. Then, okay, say you also have to report this test, right? Testing for homogeneity. And then you can now bring in your independent t-test. So once we have done that, the next thing, I think that is all. So this is just like a sample that we can use to report. We're saying the result examined the homogeneity of variance are assessed by this. And what was the conclusion? We needed to conclude. Independent was run, the data at 95% confidence interval to determine the main difference. It was found that after the two, here they were using the salaries, were significantly higher. So you see they're choosing this, right? Since we have significant value, you can go ahead and use it with significantly higher than the other group. With T, we give it a T, its degree of freedom, the actual T value is probability. When probability is less than 0.05, most often it presents it like this. 0.001, 0.001, right? So we put just like this, and it goes. So I think that's all for the independent sample t-test. Now, since we will not have break today, right? We will simply quickly discuss on the pair sample t-test. That one, I'll just tell you how to do it. You go and read the notes. If there are no notes, you go and look for notes. Is it clear? So the first thing about we have seen the independent dealing with two groups that are unrelated. Now for the dependent sample, the reverse is true. The groups are related. We may want to measure the performance of students first semester, second semester, right? So do they perform the same first year, second year, right? If you've been to UB, discover that most students they perform well final year. So, but that is an assumption. We need to verify with data. Most students will score their first A's the final year. Some always score their first A with project. That's data that needs to be analyzed. So once you do your analysis, you can now verify. So with such analysis, you said there's repeated measure because you are dealing with the same group of students, but in two different scenarios or two. And one of the most differentiating factor at times is the time. You want to conduct a study that's to do with experiment. Let's assume that we are experimenting. You can say that, okay, I'm teaching students how to use SPSS. I teach them how to use SPSS for a day. I go and spend a week, come back again. Before I even teach them, I give a test to verify their knowledge on SPSS, right? Once we've given the test to verify the knowledge, the next thing is that we can come now to so I want to, why is that the projector is not, it has gone off. Okay. Let's say before I assess their performance, I need to administer an instrument. So I give them, I share maybe questionnaires or whatsoever, I test, they perform, and I collect the results. After training, maybe 1 or 2 days, I go and spend a week, come back and re-administer either the same test or a different test. But maybe it's within to verify their knowledge. So such is study, we call it an experimental design. So we are doing the intervention study. And so with most intervention studies, we use this type of test to assess. And so you want to verify if their performance have changed significantly. Yes, there can be a small increase, but is that increase significant, right? The next thing, a possibility could be that it's a vaccine or a drug that you want to test. You select patients, you give them, and come back again to assess the same situation. The underlying idea here is that you are assessing the same situation in two different scenarios with the same persons, right? So you use the independent sample test. That's the primary, the pair sample. It's also known as dependent sample test. So the first assumption, similar to what we've seen, that the dependent variable should be continuous, right? The second assumption says the dependent variable should be categorical with two categories. There should be no significant outliers, data should be not normally distributed, and there should be correlation. Correlation here now, or relationship, which means the first group is the same group that's taking the exam the second term, right? So they should share that relationship. Instead of looking for differences, they should share relationship. That's why when you run the output, you will verify and discover that we have a possibility for us to establish a level of relationship between the groups or the two scenarios. So that's all about the independent and the best sample. How do we do it? If we can use the same data, we still give can get the same results. Maybe I can share back a screen so we see what to do. If you're there, share your screen, please.
You have to
stop mine. Am I sharing?
Yes, you're still sharing.
Okay. Then go ahead now. Okay.
So are you seeing?
Yes. Go to pet sample.
Pet samples.
Yes, samples. So let's assume that we do a simple comparative sample. We're using two subjects, English and should English go with writing? Let's take English and writing or reading and mathematics. Anyone? We just want to compare if the performance are the same using those two subjects. So that's all. You go to options, just click OK. It's to specify. Yes. Take English and writing. Do we have any significant difference between the performance of students? We see that for maths, English, they have higher performance in English compared to maths. So is that difference? The correlation is 0.2. We'll get the correlation. And the mean difference here, we are very much interested in the mean difference. What's the mean difference? The mean difference should be down. The mean difference, I can't find it.
You can see it.
I just have standard. No, I see a screen. I'm trying to establish. Okay, the mean difference same as it was for the first sample. We have our mean. Okay, this is our mean difference, which is
17.297.
With a standard deviation of this. So the approach of reporting is the same. You need to establish your descriptive, bringing in the variance, mean, and standard deviation, right? So you can give their level of similarity, which is established by correlation, and that correlation is significant. Otherwise, you can still ignore that. Then you present the mean difference for the two scenarios. We have English and French with a mean difference of this and a standard deviation of this, and that is statistically significant at 99%. The mean, I've given us a mean here. Performance in between the mean difference in performance mathematics, English and math. We use English and math as our two groups scenarios.
So yeah, I can see that the standard deviation for the English is
higher,
lower.
Yes, which means people perform more closely, closer to the mean for them English than math. You know, even in real world, what happens is that when you get to a math class, you tend to have these geniuses who score 19 on 20, and there's some of us who will obviously bring down the class average by scoring 3 on 20. So that variation is usually higher. When you get to math, almost everybody in English will struggle around. Yes, some people, but we don't have extreme low values. So in a setting where we have so many similarities in performance or in scores, the standard deviation will be lower. So we normally expect that the standard deviation should be lower for English compared to maths, right? Yes, and students should do well in English compared to maths, which should be true, because most students will run away from maths since they form part of the population, bring lower the average. But then when it gets to mathematics, we tend to have more, either we have so many persons that a good number of people will be very good in the math and a good number will be very poor, making the range, or yeah, the range should be high, and the high range means high probability of a high standard deviation. Yes. Go to analyze. Compared, see, you go to analyze here, you can still have it. I think we have analyze here. Just click the analyze here that you see. Yes. Pet sample. Go to pet samples.
Pet samples.
Yes.
Okay.
So you just need to choose the different scenarios, right?
Yes.
Variable 1, we put English, and variable 2, French. I mean math. Do you see it?
So this is it already, or we do another one?
We are trying to explain to those that are here.
Ah, okay.
You could just change and maybe remove English and put reading, or any other, yes, put reading. Let's see whether there will be. Yes, take reading and put there. Yeah, and just take, we can compare reading and writing since they are similar. At least there should be similarities. So remove maths and bring writing. So take OK. So what do we see? So many students tend to do well in writing, an average of 82 with a standard deviation of 7. I mean, in reading, when it comes to writing, the average is a bit low, and there's high variation in writing performance as compared. The correlation, the relationship between the two is very weak, but somehow significant, because less than 0.05. And what is the difference? There's not much difference in writing and reading compared to when we had English and French, English and maths, right? The main difference here is just 2.521 or 22 with a very high standard deviation, which is 9. Then if you look at the t value, it's 5, far more, above 1.968, which is our ratio, and with a degree of freedom, then it's probability. Use the probability to draw conclusion. You can use the confidence, the upper and lower bounds to also draw that conclusions. So, clear.
So you said that the correlation is kind of low. Is it not 10%?
We'll get to correlation. No, it's not.
Okay.
We'll get the correlation. Correlation range between -1 and 1. So we'll get there. So I just wanted to mention that we have not done correlation.
Oh, okay.
Effectively, we've been using it, but not done it. So, ladies and gentlemen, I think with that questions, my task for today done. We agree that this one we'll do today, right? We know break, so we have to close the like some people don't want to go home. So, Ekon, anything from your end?
No, I think the class of today is far more better than yesterday.
Because you were the one doing the analysis of it.
No.
You started getting the principle. Yesterday, some of the principles were new. So
yes,
that's why I say we keep using the words over and over, repeating. So even something you did not get, you'll get now. Yes. So it gets better with time if you go and do some reading, revise, practice. And statistics, you'll forget soon if you don't revise. So, but that's how we try to make it interactive so that as much as possible, it's not less rushing. But I still covered 1 sample, 2 samples, independent, and over in a single day, in a single class. It's possible. Put everything together and give you to drink. But it will not help most of us.
Yes.
So I think that should be all. I'm giving an assignment. There is a data set. I hope to find it. Maybe I'll share in the platform so that we'll get the data. But the assignment you're expected, it's the same principle now. Same time. Do it well. If you don't do well, submit after time. We don't consider. Don't send me PDF, please. No, submit assignment to the email. We have a standard email for assignments. So don't use my WhatsApp number. It's inefficient. We could have been sharing the content via WhatsApp. I mean, via email, but I think some of us prefer WhatsApp, which is not professional that much. And when you receive content, email, it can be there for long, unless you delete it. So WhatsApp, after 2 weeks, you will look for it, you will not find. So with that, all we do, any worry for what we have done? If there's no worry, we're expected to go and read an ANOVA. That is one-way ANOVA. I think that's the only one we'll see in this class. I don't know. I'm supposed to finish ANOVA before the other person comes in. Otherwise, I should not be here next week. At least I need to take rest for others to also come and brush. That be so. So everything being equal, I will discuss and update, but send your assignments. So I think that should be all for today's class. Econ, Madam wrote bye-bye. The others that did not show up,
Bye-bye.
I wish you a happy week.
You too, sir. Bye.